Development of Macro-Cantilever Capacitive Sensor for the detection of damages in civil engineering structures. Abstract. A modified Macro-Cantilever Capacitive sensor design is presented and used in the development of vibration sensor for structural health monitoring, SHM. The design of sensor consists of parallel feed electrode with integrated support. The overall size of the unit cell structure is 50 × 25 mm. Different civil engineering blocks were tested using the proposed sensor, and a comprehensive vibration analysis is presented based on the two-dimensional force applied to blocks. The sensor offers a lowest average sensitivity of 0.21631 pf/mm3. The proposed flex sensor can also be potentially used for the detection and monitoring of other structural parameters like stress, strain, vibration, load capacity, etc. Keywords: Macro-Cantilever sensor, capacitive sensor for vibration analysis, stress detection, civil engineering block. 1. Introduction. Minor deformation can lead to major failures in the civil and mechanical engineering structures like bridges, buildings, aircrafts, etc. These structures have multiple important or critical locations. Therefore, wireless and remote monitoring of crack formation is important in order to access the structural health and its integrity. Various physical parameters like strain, crack, moisture, and corrosion are targeted for structural health monitoring, SHM. 1,2. Microstrain sensors with optical fiber. 3. Electrical resistance electrode. 4. Piezoelectric transducers. 5. And planar capacitive interdigitate electrode, IDE. 6. 8 have been developed for strain sensing. Fiber-based sensor probes offer the highest sensitivity related to the changes in moisture content, corrosion in steel rebars, and structural deformities. But strain sensors are very costly because of its difficult embedded methodology. Furthermore, because of the perturbation of probe adjustments during the embedding process, optical sensors always have measurement errors. Piezoelectric transducers has widely been reported for SHM applications, although data received from the acoustic signal is somewhat unreliable. In this work, scaled-up design of Micro-Cantilever Sensor 9 is utilized and fabricated. It will be utilized to understand load and vibrations analogy on civil structures and corresponding effect on structural failures. 2. Development of planar Macro-Cantilever sensor. A. Design and fabrication of Macro-Cantilever unit cell sensor. The capacitive sensors can also be modeled for vibration analysis in civil engineering structures. For this, Macro-Cantilever arrangement is required. The design of proposed Macro-Cantilever is represented in Fig. The cantilever is modeled using a foam-based substrate of relative permittivity R equals 2.2 and thickness of 2 mm. The selection of flexible substrate is required so that transverse acting force can bend the positive cantilever. Moreover, large vibration dense damages the sensor plate. B. Design and fabrication of signal detection circuit and interfacing. The signal detection circuit for the flexible sensor array consists of a capacitance to voltage converter using IC-CAV424. The input capacitance from sensor and IC's internal reference capacitance are compared and converted into DC voltage. Fig 4.3 shows the schematic of converter IC. The measured output voltage from CAV424 circuit as shown in Fig 2.4, will be given to the analog port of Arduino controller for voltage measurements. Fig 2.4 circuit diagram for biasing CAV424 CV converter. The circuit is operated in differential capacitive input signal mode. In this configuration, the input capacitance, CSENS, from the Macro-Cantilever bending is compared with a reference capacitance, CREF, of 220 pF. Both capacitances are charged and discharged synchronously with a constant current by their separate integrator blocks. The charge currents for CSENS and CREF can be adjusted using R1 and R2 respectively. The time constant for the charge and discharge process is given by the oscillator block, whose frequency can be adjusted using COSC and ROSC. At the low-pass stage, the difference of these sawtooth output voltages is converted into a DC voltage. The output voltage VOUT at pin 5 is ratiometric to the supply voltage and is a linear function of 1/CSENS. It can be referenced to GND or to pin 6 to obtain the differential output voltage VDIF equals VOUT VREF. The typical values selected for biasing the circuit are discussed in Table 2.1. C. Development of sensor system. The fabricated CV converter circuit was connected to the necessary DC voltage source. The positive connection of the sensor is connected to the input capacitance pin, 14, of the CAV424 and negative was commonly grounded with circuit grounded network. The output port VOUT, pin 5, was then connected to the analog port A0 of the Arduino controller for DC voltage measurement from the sensor system. Fig 2.6 shows the complete setup of the capacitive sensor. 3 results and discussion. The measured capacitance for variation in the distance between plates of the capacitive cantilever system is plotted in Fig 4.7. In the fabricated sensor, the vibrational force from the metal joints of civil engineering structure bends the flexible macro-cantilever for short interval of time and the position get restored again. For large vibration, the cantilever touches the and VE plate and short circuit condition results in zero capacitance. As the distance increase, the capacitance reduces in a linear manner. The measured output voltage VO from the prototype sensor shows a minor decrease in the DC level as the sensor capacitance reduces or distance increase. This is because the CREF is 220 pF. In order to obtain large variation in the output voltage, a higher value of CREF is needed. It can be observed that increase of the load on the sensor is the parameter of the stress on the structure. As the stress on the structure increases, distance between positive and negative feed decreases. Distance is proportional to the capacitance or voltage. Thus, by measuring the pattern of capacitance or voltage variation over a period of time and distance can relate between stress on the structure and possible withholding capacity of the structure against the stress by identifying the failure point of civil materials. Thus, macro-cantilever-based sensory studies prove to be very significant methodology for stress and vibration study in structural health monitoring, SHM. For conclusion, a modified scaled-up design of the capacitive macro-cantilever unit cell is developed and is used to realize a stress and vibrations in various civil engineering blocks. The proposed sensor shows a considerable change in the capacitance under the unit cell where force distributions in extreme load conditions takes place on the civil structures. It is also indicative that three-dimensional sensory applications can be built to an advantage. Acknowledgement. This publication is an outcome of the R&D work undertaken in the project under the Visvesvaraya PhD scheme of Ministry of Electronics and Information Technology, Government of India, being implemented by Digital India Corporation, formerly Media Lab Asia. The authors also thank Sensor Laboratory, Electronics Engineering Department, SVNIT for providing the fabrication and testing facility.